Hello everyone, welcome to your third tutorial for ECE 457A. Today we'll be covering PSO, particle swarm optimization, and genetic algorithm. All right. So based on the flowcharts given in the lectures, the codes are written here for you, and you can find them in the same repository as before here. And let's go through the lines of code, and I'll explain to you the purpose of each line, important lines of code. And we will run the algorithms, and I'll provide you with some comparisons between the methods. Okay, so the first one is particle swarm optimization. So based on your lecture notes, first you have the candidate solution or particles that you need to initialize them. So this is the first line of code. And you're initializing each particle. After that, you set your initial global best, for which we set it to infinity, which is a high value for the cost function, which is actually the worst cost function that you can give. And after that, for every particle, you need to do a local search. So it says that every particle searches locally in a local neighborhood. We apply the local search function here. Then we get the best x and the best cost for each x. Then we need to find the local best particles for use in the velocity vector. So for the local best, we have two options. As you can see on slide number 4 of your lecture notes, for local best, you have local best of particle itself in this iteration, or local best of particle itself so far, or in all iterations until now. So if you're choosing this iteration, this line of code will run, and so far it considers all iterations until now and provides the local best for x. Then we have find the best solution of this iteration. We find the best solution of this iteration based on the history of the iterations that we got in the previous lines. After that, we have find the global best particle. Then again, for this, we have this iteration or so far. So global best of all iterations so far, like best found solution so far, or best of solutions found by particles in this iteration. This is the second option actually, and this is the first option. Then we move on to update every particle using regularization hyperparameters. So you have alpha 1, alpha 2, alpha 3. You have your local best, you have your global best found here, and the formula that then again you have them formula number 1 and formula number 2 in your slides, like page 4 of your slides. Then again, we apply the bound solution in X range function for the values that go out of bounds. So we clip them and then append them to the history and provide the best global position, global cost history, and particles. We're actually using these particles because we have modified the plot function in order to show the trajectory of each particle in both algorithms, PSO and genetic algorithm. Okay, so this is from for PSO in the config file. We have maximum number of iterations, we have number of particles, we have variables alpha 1, alpha 2, alpha 3. So alpha values must be small because the vectors may become big. And big alpha values can cause the positions or x's to go like out of the range, out of the bounds. And when they go out of the bound, we need to clip them. And because alpha values are high and the x's are out of the bound, in the next iterations we get out of the bound x's, and then we are clipping after clipping after clipping, so our position will be on the boundaries. So we're not exploring the area inside of the range or inside of those boundaries, specified boundaries. That's why we select alpha values to be small, so we can explore inside of the boundaries. Then we have local best option, so you can choose this iteration or so far for both of them, global and local. Because we're applying local search inside of PSO, we have max iteration for local search as well. And the convergence threshold for local search. Okay. Let me just double check the code just to make sure the max iteration. LS. Okay, LS max iteration. Okay, that's correct. Let's move on to genetic algorithm. Okay. So first we initialize the population. Like in PSO we had particles, here we have population, so they're the same thing. And we have some algorithm in such algorithms. We have like populations, individuals, candidate solutions, or like particles. These are the terms that can be used interchangeably. Okay, so the first line, best solution initialized, best cost, then again infinity, which is the like worst case scenario. After that, we have initialized chromosome history required for visualization. Because we want to visualize like the trajectory of each particle. So the first step here is the fitness or cost function. So we know that the cost function is negative of fitness. So here we work with cost function. So the less amount of cost function, like the better individual. Evaluate the cost of each individual in the population. Here, note that individuals are like candidate solutions. Update the chromosome history required for visualization. And find the best solution in this generation or iteration. So find the best solution in this generation based on the cost values. After that, you move on to select parents for crossover, which is the natural selection. Define the number of parents as a fraction of population size. So you have a crossover rate. For example, the number of parents is a crossover percent of the population size. Then we're sorting the indices actually for the best cost values, like better cost values, the cost values that are close to zero. Select the first number of parents indices corresponding to the individuals with lowest cost values. Then again, here we apply random natural selection. So in natural selection part, we're actually applying random selection, selecting k random chromosomes as parents. So we're selecting 2 random chromosomes as parents out of the chromosomes at the existing generation. So here you can modify the code, and you can use elitism selection. For elitism selection, you're only selecting the first 2 indices here because they represent the parents or chromosomes with the lowest cost values. Because in elitism selection, you have it defines selecting the top k chromosomes with the best fitness or cost value, but it has the risk of getting stuck in local optimum. You can use this function, np random choice, if you want to have that roulette wheel for the probabilities. You can actually represent that using the random choice. So you can use it with replacement or without replacement. Then you have a list of probabilities for each value inside this array. For example, here, yes, for this one, you can provide a set of probabilities like this. And yes, you can actually simulate the roulette wheel using this code, or use the elitism if you're selecting the first 2 options after sorting them. All right, let's move on. After that, we have yes, create offspring through crossover. So we did random natural selection. After that, we have 1-point crossover. Then mutate offspring, random changes to the offspring after crossover, and replace the old population with the new population or the offspring. Okay, so we're returning best solution, best cost, history of best solution, history of best cost, and chromosomes in order to show the trajectory of the population in the new plot. All right. In the config file, we have maximum number of iterations. So here, iterations represent generations, specify how many times the genetic algorithm will evolve the population. Then we have the population size here. We had number of particles, population size, same thing, number of individuals or candidate solutions in each generation or iteration. Then we have mutation rate, the probability that a new offspring will undergo mutation. Then we have crossover rate, the probability that 2 selected individuals or parents will undergo crossover to produce offspring. So this is actually the rate by which we're selecting an amount, like the amount of parents, some parents from the population, like 80% of the population will be selected as the parents. All right, let's move on to the plots. Let's first run PSO local best option this iteration, global best option this iteration, 500 number of maximum iterations, and number of particles 10. So here, in these codes, before we look at the graph, one thing to mention is that in PSO, we're applying the local search, but we're not doing that in genetic algorithm. So basically, PSO will be slower than genetic algorithm because of this inner local search. But there are some variants of genetic algorithm that can have local search inside of them, but we're not using those here. Okay, so this is the 3D plot. This is the 2D plot. So we have optimization path. This optimization path actually shows the best solution in every iteration. And the blue dot is the best solution. And these are the particles. So we selected 10 particles. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I think 10 is here. And this plot shows the trajectory of each particle. Okay, let's try something else. Let's use so far here in the global best option. PSO so far. Okay. One thing in the genetic algorithm is that mutation is actually doing what local search does. So it's exploiting, and crossover is exploring. So for crossover and mutation, we can use different algorithms or a combination of different ideas. Okay. One, two, three, four, five, six, seven, eight, maybe 9 and 10 here, or somewhere around here. Okay, let's try something else. Let's do so far. And, Okay, I think we didn't try this one. Okay. Um. So this plot is actually with this iteration. Okay. So global best option is selected as this iteration, and we have some like abrupt changes. Let's put it to so far. Sorry. Let's set this to so far and compare them. Mm, all right. So the thing here is that we are not seeing like those abrupt changes for so far. Like global best option is so far. Maybe we're getting the same like global best in the same direction, but when we set it to this iteration, we get abrupt changes uh, in the trajectory of the candidate solutions or the particles. So that's one thing that I wanted to mention. Now let's move on to genetic algorithm. Oh, it's running multiple. It's getting multiple runs. Okay. Maximum number of iterations 500 for the sake of comparison with PSO. Population size 10. Again for the sake of comparison. And okay. Now let's run genetic algorithm. And we're in the middle of a run. Okay, from that. So this is our genetic algorithm. This is the trajectory of the like best solution. And the trajectory of best solution in each iteration. And this one shows, yes, the trajectory of the particles. So remember that we had 10 particles, and this shows the trajectory of the particles. And these sudden changes, like these abrupt sudden changes that you see here are all because of the mutation and the crossover that is happening. So this is the reason behind these changes of the candidate solutions. And you actually saw that the run was much faster than PSO. That's because we have no inner local search. Alright, so that's it for today's tutorial. Goodbye.